boring heads, often used for making precision holes on a milling machine. They achieve that by using single point cutting tool bits, but the only one I have is this weird one. It can be adjusted by turning the inside of the holder. Also, the scale on this is barely readable and has increments of 1 mm, which is quite coarse even for a hobby machine shop. So let's make a new one. But a normal one is out of the question, because as a millennial and self-proclaimed button pusher, I need every help modern technology has to offer. I'm thinking of using the most common form and add some features to it. A LCD would be great, because I can barely see anymore. I also need a form of distance measurement. A more or less precise potentiometer would be my first choice, because I spent $30 on one and I need to use it in a project. And because I'm a dexterous cripple, a motor that increments precisely the position would be good. And because I don't like wires, everything needs to run on batteries. That should be enough pain and suffering for the moment. And with that out of the way, let's see if I can make it work, or it just disintegrates at the first cut. Now let's take a quick look at the electronics, which will make it work hopefully. Nothing special really, except for a 12-bit ADC, because the Arduino only has a 10-bit ADC, but more on that later. Before I build and design anything, I'm going to test those motors. If they're even capable of moving the mechanical parts, because they look really tiny and I don't have a lot of trust in them. As for testing them, the easiest method that I could think of would be to see how much weight they can move vertically before stalling. To get a rough idea how much weight is necessary, I'm testing the components one by one. The potentiometer is the easiest one. Just take a scale and record the maximum weight which is needed to move it. For the moving part of the boring head, the closest thing is this milling attachment that I made. The dovetails in this are comparable in size, but to get a decent result, let's first get rid of some extra weight. With that, we know that those tiny motors must lift at least 450 grams or they are not suitable. The first one can move quite fast and has already an output which creates linear motion without any additional parts. I will test them each with a voltage of 5 volts, and this one can lift 150 grams without issue. At 250 grams it starts to lose steps, and this is not good. Why am I doing this? For the second motor, I needed to machine a little gear rack of module 0.5 to create a linear motion output. Thankfully, this one is quite strong, lifting 750 grams without issue, although a bit slower than the other one. 450 grams was to be beaten, and this motor should be capable of moving the top part of the boring head without problem. At first, I wanted to power everything with a buck converter, which is stupid. They have a really high ripple voltage at the output, and this is not good if you want to utilize the whole resolution of the ADC. In this case is 11-bit, and that means I need a ripple of 3 mV or lower. So for now I'm using the fixed voltage regulator on the Arduino as a reference for the ADC. And with a floating mean value that acts as a digital low pass filter, there is no noise in the ADC value left. Not perfect, it adds latency to the system, but that is not a big concern for this use case. To test the DRO and minimize cosine errors, I tried to line up the potentiometer with the axis of the machine, which was quite tricky, and I couldn't get a good result in the end because it appears to be bent. The resolution is there, it can detect steps of 1/100th of a millimeter, but over a large distance it is not precise anymore, which can be because of the bend in it or the linearity error of the resistance. But what does the linearity error mean? For example, this resistor has an error of plus or minus 3% of linearity, which means that the resistance value can differ from the ideal value by this amount in any shape or form. It can be compensated for in software, so clearly a problem for tomorrow. And let's finally design and build something. And this is it. Every brown part is 3D printed, the body will be out of steel, and some minor parts are out of aluminium. The balance of that thing will be catastrophic, and it is quite hollow, because all of the electronics are on the inside. Hopefully it will not vibrate too much. Maybe it will be just something to look at, maybe it will work. The journey is what counts, right? Let's begin with the battery holder. It is mainly 3D printed, but it needs brass contacts to get the power from the batteries to the inside of the boring head. Printing out a template was not enough because I lack basic skills, so CNC machining it is. And there goes another saw blade. And here are those finished contacts. I lost footage where I was soldering the screw terminal, or I didn't press record, typical. I'm going to use 4 of those batteries, which will give me a total voltage of 12 volts, but not much of capacity because I put them in serial to get that high voltage. Gluing them together with epoxy was a lot of fun and hopefully will keep them together. The top part will be secured with normal machine screws, so I need heat inserts for that. I would normally prefer a captive nut, but there's just not enough room for those. Because those inserts are that tiny, I would like some kind of heat insert press. Luckily I have this Dremel stand laying around for years, and I think a bit of modification will give it a new purpose.
Oh yes.
The insert that I made is not really good. The shoulder is way too big and it is really finicky to line up those heat inserts. Maybe in the future I can find a better solution, but for now it works.
No. Fuck.
And remember, hot heat inserts are hot.
Right.
That's it for this part. Not pretty, only something a mother could love, but that's good enough for me. See you in the next part.